The air feels heavier here, not just humid, thick, dense. Every breath carries more than it should, as if the atmosphere itself has weight. You hear it before you see anything. A low, constant hum. At first, it blends into the background. Then it sharpens, layered, mechanical, alive. The sound of wings. Not one, not a few. Thousands. Something moves across the forest floor. Fast. Too fast. It slips between towering ferns and massive tree-like plants, its body low, segmented, armored. It pauses for a fraction of a second, and then vanishes again into the undergrowth. This is not a reptile, not a mammal. There are no birds here, no familiar calls, no distant roars, only movement, only silence, broken by things we don't recognize. Above, the canopy shifts. A shadow passes overhead, slow, deliberate. Then it circles back. Wings stretch outward, catching the light filtering through the thick green ceiling of this ancient forest, transparent, veined, beating with quiet power. The creature hovers, watching. Its wingspan is enormous, wider than a modern bird of prey, its body slender, but unmistakably alien. This is not a bird. It's an insect, and it's hunting. On the ground, something stirs again, a smaller creature, unaware, exposed for just a moment too long. The air snaps. A sudden dive. Precision, speed, impact. And then, nothing. No struggle, no sound, just disappearance. This forest is alive, but it doesn't feel balanced. It feels overwhelming. Everything is larger than it should be, faster than it should be, built for a world that operates under rules we no longer understand. Because this is not the age of dinosaurs. They don't exist yet. There are no towering reptiles, no apex predators we would recognize. Instead, the land is ruled by something far older, something that, in our world, we barely notice. Insects, but not as we know them. These are giants, creatures that dominate the air, the ground, and everything in between. And they are not just surviving here. They are in control. This is Earth over 300 million years ago, during a time when the atmosphere itself allowed life to push beyond its limits. A time when oxygen levels were so high, it changed the very scale of living things. And in that altered world, insects didn't stay small. They became something else entirely. Something more powerful, something more dangerous. Because before dinosaurs ever had the chance to rule this planet, something else already did. And by every measure that matters, it was worse.
To understand this world, this dense, overwhelming, almost alien landscape, we have to step back further than most people ever imagine. Not thousands of years, not even millions, but more than 300 million years into the past. Long before the first dinosaurs took their steps across the earth, before mammals, before birds, before anything that would feel even remotely familiar to us. This was the Carboniferous period, a chapter in Earth's history that doesn't just look different, it operates under entirely different rules. The continents were not where they are today. Land masses were still merging, slowly assembling into the supercontinent that would later be known as Pangaea. Sea levels rose and fell unpredictably, flooding vast regions and then retreating again. And in those low-lying regions, something extraordinary emerged. forests. Not the forests we know today. No flowers, no grasses, no trees with leaves that change color in the fall. Instead, these were dominated by giant ferns, towering horsetails, and massive club mosses that stretched upward like living pillars. The air was warm, constantly humid, saturated with moisture, and thick, because the atmosphere itself was different. Oxygen levels during this time were significantly higher than what we experience today, reaching up to 30, even 35% in some estimates. That's far above the modern level of about 21%. At first glance, that might not seem like a dramatic shift, but in biological terms, it changes everything. Oxygen is not just something animals breathe. It determines how energy flows through living systems. It sets limits on size, movement, and metabolism. Increase it, and those limits begin to stretch. In this world, they stretched farther than ever before. The forests themselves played a role in this transformation. These vast wetlands were incredibly efficient at pulling carbon dioxide out of the atmosphere and releasing oxygen through photosynthesis. And when these plants died, many of them didn't fully decompose. Instead, they were buried. Layer upon layer of organic material locked away beneath sediments, preventing carbon from returning to the atmosphere. Over millions of years, this process would help create the coal deposits we still extract today. But at the time, its immediate effect was something else entirely. It enriched the air. And that enrichment created opportunity. Because while plants reshaped the atmosphere, animals began to respond to it. On land, vertebrates were still in their early stages, small, limited, not yet dominant. They had only recently begun to explore terrestrial environments, and they lacked the adaptations that would later allow reptiles and eventually dinosaurs to take control. So the land was open, unclaimed, and something else moved in to fill that space. Arthropods. Creatures with exoskeletons, jointed limbs, and segmented bodies, ancestors of modern insects, spiders, and crustaceans. In today's world, they are everywhere, but mostly small, often overlooked, rarely seen as dominant forces. But here, in the Carboniferous, they were different. They weren't hiding beneath leaves or crawling unnoticed in the soil. They were visible, prominent, and increasingly enormous. This was not an ecosystem where insects played supporting roles. They were central. They filled niches that, in later eras, would be occupied by reptiles, birds, and mammals. They moved through the air, across the forest floor, and within the dense vegetation as both predators and prey. And without large vertebrates to compete with them, their influence spread unchecked. But there's something deeper here, something that makes this world feel so unfamiliar. It's not just the size of these creatures, it's the fact that the entire system lacks the balance we expect from modern ecosystems. This is a world still experimenting. Evolution has not yet settled into stable patterns. Food webs are still forming, interactions still shifting, roles still being defined. It's dynamic, unpredictable, and in some ways, unstable. Because when conditions allow life to expand beyond its usual limits, it doesn't always lead to equilibrium. Sometimes it creates extremes. And this world, this oxygen-rich planet, this insect-dominated world, is one of those extremes, a version of Earth that was never meant to last. But for a time, it didn't just exist, it thrived.
To understand how this world became so extreme, so unfamiliar, we have to move beyond what we can see and look at the invisible forces shaping it. Because nothing about this ecosystem was accidental. It was built piece by piece by biology responding to a planet that had changed the rules. And at the center of it all is a simple question: how do you breathe? For most animals alive today, the answer is straightforward. Air enters the body, oxygen is absorbed through lungs, and then transported by blood to every cell. It's an efficient, scalable system, one that supports large, active bodies. But insects don't work that way. They don't have lungs. Instead, they rely on a network of microscopic tubes called trachea, tiny channels that run throughout their bodies, delivering oxygen directly to their tissues. There's no pump, no heart moving oxygen around, just diffusion. Oxygen enters through small openings in the exoskeleton and slowly spreads inward. It's simple, efficient for small bodies, but it comes with a hard limit, because diffusion only works over short distances. The larger the body, the harder it becomes for oxygen to reach the innermost cells. Eventually, size becomes a barrier that biology can't overcome. In today's atmosphere, that limit keeps insects small. But 300 million years ago, that limit didn't exist in the same way, because the air itself had changed. With oxygen levels rising to 30% or more, the gradient driving diffusion became far stronger. Oxygen could travel deeper into tissues, faster and more efficiently. Suddenly, the constraint that had always held insects back began to loosen, and evolution took advantage of it. Bodies grew larger, wings expanded, exoskeletons thickened to support increasing mass. This wasn't a gradual shift over hundreds of millions of years. In geological terms, it happened quickly. The fossil record reveals creatures that seem almost exaggerated, like nature pushing boundaries just to see how far it could go. Take one of the most striking examples, a creature known as Meganeura. At a glance, it resembles a modern dragonfly, but only at a glance, because its wingspan stretched to over 70 centimeters, larger than many birds flying today. Its eyes were large, optimized for detecting movement. Its flight was agile, precise, and it was a predator. It didn't just exist in this environment, it dominated the skies. Below, on the forest floor, another giant moved more slowly but with equal presence, Arthroplura. A massive, many-segmented arthropod, often compared to a millipede, it could grow over 2 meters in length, making it one of the largest land invertebrates to ever exist. It likely fed on plant material, moving steadily through dense vegetation, too large for most threats to challenge. But not everything here was slow or passive. Predatory arthropods evolved alongside them, creatures with powerful mandibles capable of seizing and crushing prey. Some hunted actively, others ambushed, and without large vertebrates to compete with them, these arthropods occupied roles across the entire ecosystem. They flew, they hunted, they scavenged, they decomposed. They were not part of the system, they were the system. And that's what makes this world so unsettling, because ecosystems today are structured, balanced at least to a degree. Predators regulate prey populations, competition limits dominance, energy flows through defined pathways. But here, those systems were still forming. There were no large reptiles yet, no birds, no mammals. Vertebrates existed, but they were small, limited, still adapting to life on land, which meant something critical was missing: competition. Without strong competitors or established predators to keep them in check, arthropods expanded into every available niche. And when a single group expands without constraint, it doesn't just grow, it takes over. The skies, once empty, became filled with winged hunters. The forest floor, once open, became crowded with massive, armored bodies. Every layer of the ecosystem, air, land, and the spaces in between, was occupied by organisms operating at a scale we no longer associate with insects. And yet, despite this dominance, there's something fragile about it, because this entire system depends on a very specific condition: high oxygen. Remove that, and everything changes. But there's more, because oxygen didn't just allow size, it amplified intensity. Higher oxygen levels increase metabolic potential. They allow organisms to generate more energy, to move faster, to react quicker. This wasn't just a world of bigger creatures, it was a world of more active ones, more aggressive interactions, more energy flowing through the system. And with that comes instability, because high-energy systems are powerful, but they are also sensitive. Small changes can have large effects, and in a world where evolution is still experimenting, still searching for stable configurations, that sensitivity becomes a weakness. What we're looking at is not a perfected ecosystem, it's an extreme one, a version of Earth pushed to its limits, where the atmosphere allowed life to grow beyond its usual constraints, and in doing so, created a world that feels almost too intense to last. Because systems like this, no matter how dominant they appear, carry within them the seeds of their own collapse. And the moment conditions begin to shift, the very traits that made these creatures successful become the reason they disappear.
It's easy to look at this ancient world and see it as something distant, a strange, almost alien version of Earth, filled with oversized insects, unfamiliar forests, and ecosystems that no longer exist. A curiosity, a spectacle. But that perspective misses something important, because this world is not disconnected from ours. In many ways, it created it. The forests that dominated the Carboniferous period were not just vast, they were transformative. Stretching across enormous regions of the planet, these dense wetlands acted like planetary engines, pulling carbon dioxide out of the atmosphere at a scale rarely seen before or since. Through photosynthesis, they released oxygen, not gradually, but persistently, year after year, century after century, for millions of years. And as plant life expanded, something unusual happened. When these plants died, they didn't fully decay. Microbial life at the time lacked the ability to efficiently break down certain complex compounds, especially lignin, a key component of woody tissue. As a result, massive amounts of plant material accumulated, layer upon layer, buried under sediment and water. That buried carbon didn't return to the atmosphere. It stayed locked away. Over time, under pressure and heat, it transformed into coal. The same coal that would be extracted hundreds of millions of years later and burned to power industrial societies. Which means the energy we use today, the electricity in our cities, the fuel that drives industry, has its origins in this ancient world, a world of giant insects, a world shaped by extreme oxygen levels, a world that at first glance seems completely unrelated to modern life. But the connection runs deeper than energy, because what happened in the Carboniferous period is one of the clearest examples of how life and the atmosphere shape each other. Plants changed the atmosphere changed animals, and those animals in turn influenced ecosystems in ways that fed back into the system. It's a loop, a continuous interaction between biology and environment, and it hasn't stopped. Today, we are part of that same loop, but now the direction of change is different. Instead of removing carbon from the atmosphere, we are releasing it rapidly at a pace far faster than natural systems typically operate. By burning fossil fuels, those ancient carbon stores, we are effectively undoing part of the transformation that began in the Carboniferous. Carbon that was locked away for hundreds of millions of years is being returned to the atmosphere in just a few centuries. And as that happens, the balance shifts again. Temperatures rise, climate systems adjust, ecosystems respond. This is not speculation. It is a measurable process, studied by institutions like NASA and NOAA, tracked through atmospheric data, ice cores, and long-term climate models. But the deeper lesson isn't just about climate change. It's about sensitivity. The Carboniferous world shows us that life can expand dramatically under the right conditions, but it also shows how dependent that expansion is on those conditions remaining stable. The giant arthropods didn't evolve into massive forms because they were inherently superior. They evolved that way because the environment allowed it. And when that environment changed, their advantage disappeared. This pattern appears again and again throughout Earth's history. Conditions shift, life adapts, dominant groups rise, and then inevitably, those conditions shift again. The idea that any species, no matter how successful, can remain dominant indefinitely is not supported by the history of this planet. And that includes us. Because while humans are fundamentally different from giant insects, our biology, our intelligence, our technology, we are still bound by the same underlying systems. We depend on a stable climate, on predictable ecosystems, on atmospheric conditions that allow agriculture, infrastructure, and complex societies to function. Change those conditions and everything else begins to shift, slowly at first, then all at once. The Carboniferous period is not just a story about giant insects, it's a case study in how environmental change reshapes life, how abundance can lead to extremes, and how those extremes can become fragile. There's also another layer to this connection, one that's more subtle. The way we understand this ancient world comes from evidence preserved over immense spans of time. Fossils embedded in rock, chemical signatures locked within minerals, geological formations that record changes in climate and atmosphere. Scientists reconstruct this past using tools from paleontology, geology, and geochemistry, disciplines that together allow us to read Earth's history like a record. And what that record shows is not randomness. It shows patterns, cause and effect, feedback loops, systems interacting over vast timescales. Which means the story of giant insects is not just a strange anomaly, it's part of a larger narrative, one that continues today. Because the same forces that shape that world, carbon cycles, atmospheric composition, ecological balance, are still active, still influencing life, still determining what is possible and what is not. So when we look at that ancient forest filled with creatures that seem almost impossible, we're not just looking into the past, we're looking at a version of Earth responding to change. And in that reflection, there's a question that becomes difficult to ignore. If altering the atmosphere once allowed insects to become giants, what will altering it now allow or prevent next? Because the system hasn't stopped, and neither has the process of change.
For millions of years, this world held together. Dense forests stretched across continents. Oxygen levels remained high. Arthropods grew to extraordinary sizes, filling the air and land with forms that even now feel almost impossible. It looked stable. It felt dominant, but it wasn't permanent, because the very conditions that allowed this world to exist were also quietly shifting beneath it. The first changes were subtle. Tectonic forces continued to move continents, gradually assembling them into larger land masses. As these shifts progressed, global climate patterns began to change. Regions that were once humid and waterlogged started to dry. The vast swamp forests, so critical to maintaining high oxygen levels, began to shrink. Less forest meant less carbon being locked away, and slowly, the balance of the atmosphere began to tip. Oxygen levels declined, not suddenly, not catastrophically, but steadily enough to matter. At the same time, new biological processes were emerging. Microorganisms evolved that could more effectively break down plant material, including lignin. What had once accumulated as thick layers of undecomposed organic matter now began to decay more efficiently. Carbon that would have been buried returned to the atmosphere. The system was adjusting, and with that adjustment came consequences. For the giant arthropods, this change was not abstract, it was physiological. Their entire existence depended on a high oxygen environment. Their tracheal breathing system, so effective in an oxygen-rich world, began to reach its limits again. As oxygen levels dropped, diffusion became less efficient. Large bodies could no longer be sustained in the same way. The deeper tissues of these giants struggled to receive enough oxygen. Movement became more costly. Growth became constrained. Reproduction became less viable at larger sizes. The very trait that had defined their dominance, size, became a disadvantage. This is how collapse begins. Not with a single event, but with a shift in constraints. What was once possible is no longer, and evolution responds. Smaller individuals survive more easily. Energy demands decrease. Efficiency becomes more important than scale. Over generations, size reduces. Diversity declines. The giants disappear. But the transformation doesn't stop there, because as one group loses its advantage, another begins to gain one. In this changing world, vertebrates were quietly evolving. early reptiles, descendants of amphibian-like ancestors, had begun to develop a key adaptation, the amniotic egg. Unlike amphibians, which required water to reproduce, these early reptiles could lay eggs on land, freeing them from dependence on aquatic environments. This single innovation changed everything. As the climate became drier and forests receded, these reptiles were better suited to survive and expand. Their lungs allowed more efficient oxygen intake. Their circulatory systems supported larger, more active bodies, even as atmospheric oxygen levels declined. They were not constrained in the same way as arthropods. Where insects began to shrink, reptiles began to grow. Where one system reached its limit, another found opportunity. This is the turning point. Not a sudden overthrow, but a gradual replacement. Ecosystems reorganized, food webs restructured, roles shifted. The world that had once been dominated by giant arthropods gave way to a new balance, one in which vertebrates would increasingly take control. And over tens of millions of years, that trend continued. Reptiles diversified. Some lineages grew larger, more specialized, more dominant. Eventually, this evolutionary path would lead to the rise of dinosaurs, the creatures we most often associate with prehistoric Earth. But by the time dinosaurs appeared, the world of giant insects was already gone. Not because it failed in a dramatic sense, but because it depended on conditions that no longer existed. This is the deeper revelation, that dominance is not about absolute strength or even superiority. It's about alignment. Alignment with the environment, with the chemistry of the atmosphere, with the structure of ecosystems. The giant arthropods of the Carboniferous were perfectly adapted to a world with high oxygen, dense forests, and limited competition from vertebrates. Change those conditions, and their advantage disappears. This pattern is not unique. It repeats throughout Earth's history. The Permian period that followed would end in the largest mass extinction the planet has ever experienced, wiping out the majority of species and reshaping life once again. Later, the dinosaurs themselves, after dominating for over 160 million years, would vanish in another extinction event, making way for mammals. Each time, the story is similar. A group rises, adapts, dominates, then the environment shifts, and a new group takes its place. The Carboniferous world feels strange because it breaks our expectations. We don't imagine insects as rulers of ecosystems. We don't imagine dragonflies the size of birds or millipedes the length of a car. But that discomfort comes from our perspective, shaped by the present. In reality, that world was not an anomaly. It was one of many possible outcomes, a version of Earth responding to a specific set of conditions. And when those conditions changed, so did everything else. The giants didn't disappear because they were weak. They disappeared because the rules changed. And in a system as complex and interconnected as Earth's biosphere, when the rules change, no amount of dominance can guarantee survival.
When we look back at this world, this dense, oxygen-rich planet filled with towering forests and giant insects, it's easy to see it as something distant, something strange, almost unreal. A version of Earth that feels more like imagination than history. But the deeper truth is far more unsettling, because this world was real. It existed under the same laws of physics, the same chemistry, the same evolutionary processes that govern life today. Nothing about it was impossible. It was simply different. Different conditions, different balances, different outcomes. And that difference is what makes it so important, because it forces us to confront a simple idea. The world we know now is not permanent. It feels stable, predictable, familiar. But so did that world. For millions of years, the Carboniferous Earth supported vast forests, high oxygen levels, and ecosystems dominated by creatures unlike anything we see today. To the life forms that existed then, that world was normal. It was the only world they had ever known. And yet, it didn't last. The forests receded, the atmosphere changed, the giants disappeared. Not because of a single catastrophic moment, but because the conditions that supported them slowly shifted beyond the limits they could tolerate. And when those limits were crossed, dominance meant nothing. This is the pattern that runs through all of Earth's history, not just in the age before dinosaurs, but in every age. Life rises within a set of conditions. It adapts to those conditions, often becoming highly specialized, perfectly tuned to the environment it inhabits. But that specialization comes with a cost. The more adapted a species becomes to a specific world, the more vulnerable it becomes when that world changes. The giant arthropods were not flawed organisms. They were extraordinarily successful. They filled every niche, expanded to incredible sizes, and dominated their ecosystems completely. But they were tied, completely, to a high oxygen environment. When that environment shifted, they could not follow. And so, they vanished. This is not a story about failure. It's a story about limits. Limits imposed not by biology alone, but by the interaction between life and the planet itself. Because Earth is not a static stage on which life performs. It is an active system. A system that responds, evolves, and changes, sometimes gradually, sometimes abruptly. And life must respond with it. The rise of reptiles after the Carboniferous is not just an evolutionary milestone. It is a reminder that when conditions change, entirely new forms of life can emerge, forms better suited to the new reality. Later, the dinosaurs would rise and dominate for over 160 million years. They too would seem unstoppable. They too would define what it meant to rule the Earth. And yet, they are gone, replaced by mammals, and eventually by us. Each time the pattern repeats, dominance feels permanent until it isn't. And that brings us back to the present. Because for the first time in Earth's history, a single species is not just adapting to the environment, it is actively reshaping it. We are altering atmospheric composition, changing climate systems, modifying ecosystems at a global scale. In doing so, we are influencing the same variables that once allowed insects to become giants and later caused them to disappear. But there is a critical difference. The changes that shaped the Carboniferous world occurred over millions of years. What we are doing is happening in centuries, a pace that is, in geological terms, almost instantaneous. And that raises a question that goes beyond science. It becomes philosophical. What does it mean to be dominant in a system that is constantly changing? Is dominance about size, strength, intelligence, or is it something else entirely? Because if there is one lesson that echoes from that ancient world, it is this. Earth does not reward permanence, it rewards adaptability, the ability to respond to change, to shift, evolve, and survive as conditions transform. The giant arthropods could not adapt fast enough to a declining oxygen world. The dinosaurs could not survive the aftermath of a global catastrophe. And now we exist in a moment where the pace of change is accelerating once again. But this time, the source of that change is us. We are not passive participants in the system. We are active drivers. And that places us in a position unlike any species before. It gives us awareness, the ability to understand patterns, to study the past, to predict possible futures. But awareness does not guarantee action, and it does not guarantee survival, because the rules that govern the Carboniferous still apply. Change the environment, and life must respond. The question is not whether Earth will continue. It will. It always does. The question is whether the conditions that support us will remain within the limits we can tolerate, or whether, like the giants before dinosaurs, we will find ourselves perfectly adapted to a world that no longer exists. When we look at those ancient forests, at the shadows of massive wings moving through dense, humid air, we are not just looking at lost world. We are looking at a possibility, a reminder that Earth can become something very different from what we know, and that what feels normal today is only temporary. Because long before dinosaurs ruled this planet, something else did. It thrived, it dominated, and then, quietly, it disappeared, not with a roar, but with a change in the air.